Hiya. So now we're going to look at this skewness correction factor, this approximation, and kind of see how this works in an actual example to kind of see what's happening. So what I want to do in this case is I'm going to take, what am I doing? The distribution of zeros and 100 randomly selected digits. So basically I have some string of digits, so 100 of them, and they're all numbered 0 through 9. So it doesn't matter what the numbers are, they're just randomly selected. So each digit is any number from 0 to 9. And then the question becomes, well, okay, I want to calculate the distribution of zeros. So I want to know how many zeros there are in this string of 100 digits. And so I'm going to ask is, well, what is the probability of getting 4 or fewer zeros? So I only want to know, like, what's roughly the probability of getting 4 or fewer zeros. So we're going to do this do this in 3 different ways. We're going to look at the actual value, we're going to look at the approximation, and then we're going to look at the skew normal approximation as well, to kind of see where this comes into play. So what do we have? What we have here is p is equal to 1 over 10, right? There's 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 digits. And 0 is just one of them. So 1 out of 10 is what will set the probability out. And the question is, so that's the probability of getting a thing. Our sample space, right, for each digit is given by the numbers, all the numbers. Right, so this is why we have 1 over 10. We're doing this run 100 times. So here we know that n is equal to 100 because we have 100 digits. So you can think of each digit as a certain trial. So what other things we know? We know mu is equal to np, which is 100 times 1 over 10, which is equal to 10. We might as well calculate what our sigma is. Sigma is equal to np 1 minus p, which is square root of 10 times 9 over 10. So it's square root of 9, which is 3. Then we can calculate skewness of np because we're going to need this as well. This is 1 minus 2p over sigma. So we have 1 minus 2, 1/10 divided by 3. So here we have 1 minus 1/5 divided by 3. So it's 4/5 divided by 3. Flip it and reverse it. We get 4/5 times 3, so 4/15. Okay, so step 1. Let's look at the actual value. How much space do I have? Okay, cool. We'll do actual value first. Actual value. Let me first rewind this. We're going to do this because I think if I were to do this now, yes, we're going to copy this. I'm going to put it down here too. Yeah, because we'll need this in the future. It'll be easier. Okay, so we'll put this there. Okay, so actual value. So let's calculate the binomial distribution. So binomial distribution. Okay, so this, remember what we have is p from 0 to 4, right? Because we want 0 to 4 getting 4 or fewer zeros. So 0 to 4 is basically the number of digits, the number of zeros we're looking for. This, well, each particular one, right, is going to be done by 100 choose k, 1 over 10 to the k, 9 over 10, so this is 1 minus p, to the n minus k, so 100 minus k, right? And we have to do it over all of our k's, so all of our k's is from 0 to 4. So we want to see the number of 0 zeros, the number of 1 zeros, the number of 2 zeros, the number of 3 zeros, the number of 4 zeros. We add them all together. And then if you do it this way, what you end up getting is 0.024. Obviously, you can kind of see this is nasty, right? We don't necessarily want to do these. This is why we want to look at we want to look at approximations so that we don't have to sit here and do these calculations every single time. So now let's look at the normal approximation. So normal approximation. And so here, remember what we want to calculate is phi of b plus 1/2 minus mu over sigma minus phi of a minus 1/2 minus mu over sigma, right? So what's our a and what's our b? In this case, our b is 4, right? Because this is the max. And our a is 0. So what I'm going to do is we're going to just replace the b with a 4, and we're going to replace the a with a 0. And we're going to calculate. We know the mu, right? So we know mu here is equal to 10. So we can remove the mu part. We can remove the mu part. Why is this not erasing? Oh, there we go. We can remove the mu part, which I need to put 10. Sorry. And then finally we can remove the sigma part. Why is it being weird right now? And sigma we said is 3. So we can put 3's in to kind of calculate what happens. So here what we end up getting is, if you calculate this, we get 11/6 or minus 11/6. If you calculate this, so this is a minus 11 over 6. This is a minus 21 over 6. I won't calculate this. This should be an easy check for all of you. So we get this. Each one of these, since it's negative, remember we have to kind of do this negative trick. This is 6, not 0. 1 minus phi of 21 over 6. Now, if you go to the appendix and look up these numbers, we get this. Minus 1 minus 0.9998. And so here we have 0.0336 minus 0.0002, which is equal to 0.0334. You'll kind of notice the 0.334 is nowhere near the 0.024. And it's not that good of an approximation. And p is only 1/10. So let's see how this skewness factor, whether this actually helps us or kind of what happens when we look at the skew factor. So let's look at skew normal, and let's see how close we get to the actual value. So here we do the same thing. Remember here we had that the approximation is already given to 0 to b successes. So we can go straight to b. So what we end up having is the following formula. Skew NP, z squared minus 1 phi of z. Right, so what's our z here? Z is, remember, b plus 1/2 minus mu over sigma. So this we calculated above, right? So we already know that this is equal to minus 11/6, right? So this is just this part here. So it's minus 11/6. So let's plug this in. So we get phi of minus 11/6 minus, well, we take 1/6. We already know skew as well, right? We already calculated skew. This is 4/15. So here we can do 4/15 for skew times 4/15. Then we're going to do z squared minus 1. So here we have minus 11 over 6 squared minus 1. And then we need to calculate phi of minus 11 over 6. Okay? So let's see. Let's see what we have. And I guess I'm running out of room, so we're going to have to do this short. This little part here we also calculated. This part. We did this in the last one. This is just here, 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 this. So we end up with 0.00336. Okay, so what we get in this part here is we get, it looks like 2 over 45. So minus 2 over 45 is this little part here. The second part, this, if you calculate, you'd get 121 over 36 minus 36 over 36. And then we'll plug in phi. So we get square root of 2 pi e to the minus 1/2 z squared. Okay, so let's put these together. 0.0336 minus, let's multiply these kind of portions here. That we end up getting is 17 over 162 square root of 2 pi. And then as the exponent here, we get roughly, or not roughly, we get exactly minus 121 over 2 times 36. So plugging these into a calculator, we get 0.041863 times the e part gives me 0.18627. And again, plugging this into the calculator, we end up getting 0.0258. And here you'll notice this is much, much closer to our actual value of 0.024. So you can see this normal skew approximation is significantly better at approximating the binomial distribution. As you can see, so in the next video, we're going to look at a different approximation, which is called the Poisson approximation, and we'll go from there. So I'll see you in the next video.